Hello, Chem 2. Hopefully everybody is being safe and socially distant. Today we're going to talk a little bit about the Chapter 10 information from the aqueous stoichiometry unit, which revolves around different concentration units. We already know about molarity, as that mole per liter, but we're going to introduce mole fraction, mass percent, molality, and parts per million, parts per billion in passing. We've already seen part per million, and mass percent, but they're all in the same section. So here we go. So this chapter is chapter 10. It's on solutions, and it covers a lot of information, but the very first section discusses the different ways to calculate concentration for different purposes. The rest of the information there, the principles of solubility and colligative properties, that all will fall into AP Chem. But for this chapter, I just want to cover the different ways to determine the concentration of a solution. So section 1 is all we're going to do. And it starts off by reintroducing the concept of molarity. And molarity is moles of solute, that's the stuff that's being dissolved, per liter of solution, that's the stuff that's doing the dissolving. Sorry, that's the entire mixture when you're done. And they talk here really quickly about the dilution equation, which I discussed in the last video, where you have MV equals MV, but they use the C and D, whereas we used stock for the concentrated version and D for the dilution. So it's the same thing, and it is talk a little bit about what molarity is, moles per liter. And then they also introduce really quickly, just like we did in the last video, how to make a concentrated solution where you take some volume out. They took 50 mils here of a 2 molar solution, added it to another container that had exactly 1 liter in it to make a lower concentration of 0.1 molar solution of the copper sulfate. Okay, so let's talk about those other units. So the first one that's probably the one that's least used, but will be used a little bit in the next chapter, is the concept of mole fraction. Mole fraction is simple. It's kind of like a percent, but not a percent. You'll see with the example they talk about a mole fraction percent, but a mole fraction is a number that is simply the decimal equivalent of the number of moles of some substance in the solution divided by the total moles of everything that's in the solution. This is used a lot for gases where it's really tough to figure out what the solvent and the solute is. So they look at the two different numbers, the moles of whatever the component you're talking about and the total moles in there. And of course, if you were to calculate the mole fractions of all the components, it has to add up to be 1 because the total moles is the total moles. So let's look at an example. Hydrogen peroxide is used by some water treatment systems and also is used for medicine to remove disagreeable odors of sulfides in drinking water. If you can get a commercially available 30% by mass aqueous solution of hydrogen peroxide, which is really tough to get unless you go to a beauty salon store right now, the stuff you get in the store is only 3%. They're asking, what is the mole fraction of hydrogen peroxide in that sample? So this is 30% of the total mass. 30% of the total mass is hydrogen peroxide. So if we know that of the solution, it's a 100 gram sample, which we're going to assume 100 gram sample to deal with the percent issues, 30 grams of it is going to be hydrogen peroxide. That means the remaining 70 grams is going to be water. Okay, just a hydrogen peroxide solution that is 30% hydrogen peroxide, and the rest is water. The total 100 grams of solution. So in order to get mole fraction, you have to determine the moles of each of the components. So if you look at the moles of water, 70 grams at 18 grams per mole, you get 3.88 moles. But the hydrogen peroxide just says 30 grams at a larger, because hydrogen peroxide has 2 oxygens, a larger molar mass of 34 gives you 0.82 moles. So in order to get the mole fraction, you're going to take the number of moles of the hydrogen peroxide and divide it by the number of moles of the total. So get the total, divide in, and you find that the mole fraction of hydrogen peroxide is 0.185. Pretty low, but one of the things to realize is if you think in terms of mole fraction percent, which is another calculated value of mole percent, that this stuff is 18.5% of the number of moles is hydrogen peroxide. Well, that's different than 30% by mass. Well, that's because hydrogen peroxide has a larger mass than water. So that would make sense. It would have a smaller percent of the moles. Anyway, that's mole fraction. Mole fraction is moles of whatever the component is divided by the total number of moles in the solution. The second example calculation, second concentration unit is mass percent or parts per million or parts per billion, ... And we've seen this before, so we can do this one pretty quickly. Mass percent or parts per million or parts per billion is the mass of whatever thing is being dissolved, the mass of the solute, divided by the total mass. And if it's cent meaning 100, you would multiply times 100. If it were per million, parts per million, you would multiply times a million. If it was per billion, you would multiply times a billion. So again, we've seen these back in the dimensional analysis chapter, different units of percent. So if you want to have a solution that's prepared by taking 24 grams of sodium chloride and putting it into 152 grams of water, in order to figure out the mass percent, it's 24 grams of sodium chloride divided by the total grams of material. That's the 24 plus the 52. And the solution has to be 14%. And like I said, if the concentrations get to be really, really small, very, very small, that's when you start using the part per million, part per billion, because you get, instead of multiplying times 100, you would multiply times a million or a billion. Just gives you more realistic numbers to work with. Again, the concept is no different than using a parts per, that's using a percent. The next one that I want to discuss is the concept of molality. Molality, that sounds a lot like molarity, but it's molality, but it's very, very similar. It is moles of solute, that's the same. But the other part is, instead of dividing it by the liters of the solution, you're going to be dividing it by the kilograms of the solvent. This is often used when it's very difficult to know what the total volume or the total mass of the whole solution is. So if I were just to measure out a set number of grams of something, and I know the grams of whatever I'm dissolving it into, molality seems to be a little more appropriate measurement rather than trying to worry about the total solution's volume. So let's look at an example. Okay, so glucose is a compound that is often used in IVs. It is sugar, and so it's put in there in a small amount. And it says down here that what a pharmacist will do who might normally prepare it would be take a little bit of sodium, which we're not worried about here, and then add 6 grams of glucose to 112 grams of water. So 6 grams of glucose and 112 grams of water. So both are measured on a mass or a balance. So determine the molality of the solution. So since molality is moles per kilogram, what we need to do is convert our solute from grams into moles and convert our solvent from grams into kilograms, and then plug it into the equation. So first things first, numerator is glucose, 6 grams, about 180 grams per mole, gives you 0.0333 moles. And then the denominator is changing your grams into kilograms. So you take your 112 grams at 1,000 grams per kilogram, get 0.112 kilograms, and then plug it into the equation of molality, moles of glucose per kilograms of water, 0.0333 divided by 0.112, you get a molality of 0.297 molal. Just tells you this is a pretty small amount, a little over 30% of the moles to kilogram ratio. And it's weird because it does relate mass and number of moles, but it gets used in a lot of the colligative properties. You guys come to AP, we'll talk a little bit more about some of the applications of using the molality as opposed to the molarity. We'll use molarity a lot more in chem too. Anyway, so the last piece of this video talks about how to go between the various conversion units. Sometimes what you want to be able to do at the end of this section is to be able to be given one of the concentration units and be able to solve for all the rest. So one of the helpful pointers is to think in terms of if I have any other ones, where would I start? Where would I start? So for mass percent, because it's percent, it would make sense that you would start with 100 grams of solution. Therefore, the mass, say like we had 12%, that'd be 12 grams of the other things compared to 100 grams total of the solution. And you can play around with the math a little bit. For molarity, since molarity is moles per liter, you would start with 1 liter of solution. Look at what's happening. We're turning it into the per part, percent 100 grams, per liter, use 1 liter. Molality is per kilogram, so we would start with 1,000 grams or 1 kilogram of solvent. And as mole fraction, then we would start with the denominator of the mole fraction, which is the moles total, saying that the total number of moles was 1. And then break everything else down from that. Let's look at an example of how we do that. Okay, so we're going to do an example here. It asks you to calculate the molality of a solution, some compound they're going to give you that happens to have a molar mass of 100. Going to make the math a little bit easier. And that solution is 1.35 molar, 1.35 moles per liter, and it has a density of 1.28 grams per mil. You're going to see this density being given to you because in order to go from volume to mass of a solution, you need a density. And according to the definition of molarity, since we know what molarity is, that means that I have 1.35 moles of solute in 1,000 milliliters of solution. So if we're going to use this table to organize our thoughts. So if we're given the molarity, we're going to fill in the mole section for the solute and the volume section. So right now, we'll put it in that table in a second, 1.35 moles here and 1,000 milliliters or 1 liter down here. If we had molality, we would fill in the moles and the mass of the solvent because the mass of the solvent is 1,000 grams. If we had mole fraction, these two we'd be using, and if we had mass percent, we'd be using these two. Just a way to get things started and recognize what you're going to add to each one of those sections. Getting around this table, I think you should realize that it's pretty obvious that go between mass to moles. We need to use the molar mass of whatever the substance is. A lot of these times the solvent is going to be water unless it's clearly designated. So the molar mass here that we would use to go from mass to moles in the solvent section would be using the molar mass of water. And then, like I said, in order to go between volume and mass, we are going to need to use the density. So let's look at this example. So the example that we were given, the 1.35 moles per liter, we have 1.35 moles in the solute section, and we have the 1,000 milliliters in the volume. So I want to figure out what the molality is. So first thing I'm going to do is I'm going to change my mass of my solution into grams. So I'm going to use the density to go from milliliters to grams. So now I know the mass of my solution. Then I'm going to determine the mass of my solute. Again, they said it was 100 grams per mole, so I knew I have 1.35 moles. And then I have to figure out the mass of the solvent. So let's look at this. So what I've done is I've taken my 1.35, that's going to turn 135 grams. I'm going to take my 1,000 milliliters, that's going to be the 1.28 grams per milliliter, so I have 1,280. The difference between these two is the mass grams of the solvent. So in order to get molality, I'm going to take my moles, which was given to me as part of my original thing, and then I just had to go through all that little bit of work to figure out the number of grams of solvent, since the denominator is the mass of the solvent, not the solution. So I got 1.145 kilograms. So my solution that was 1.35 molar is 1.18 molal. Different concentration because of different units. The more water you have in the solution, the less concentrated it is, the closer your molarity and your molality are going to be to one another. Okay, let's look at one last situation where we're going to go through and check out all the possible ramifications. So here, this is a typical question that you might get where you're going to be asked to go between all of them. So I have a mass percent of 28.5% potassium carbonate, and the solution's density is 1.16 grams per mil. I want to calculate the molarity, the molality, and the mole fraction given the percent. Calculate everything given the percent. So let's do them one at a time. Let's start by filling in the table. We have 28.5% potassium carbonate. That means I have 28.5 grams out of a total of 100 grams. So if I do some quick math, okay, it's not really that quick math, I can figure out the number of moles I have of the solute moles I have of the solute, I calculate the the molar mass of potassium carbonate. So I know I have 0.206 moles of solute. And since molarity is moles per liter, I need to convert from my grams into my volume. And again, from our previous example, I showed you that the way to do that would be to use the density. In this case, the density was 1.16 grams per mil. I have 86.2 milliliters in that 100 grams of sample. And then finally, I have my moles. I have my volume. It's in milliliters, though. I need to convert. So I'm going to go ahead and put my numbers in. Moles, 0.206. Volume has to be in liters for molarity. So it's 0.0862 liters. Do the math, and I get that the solution is a whopping 2.39 molar. Next, I want to try to calculate my molality. Molality is moles per kilogram. So now I have to fill in this spot right here, the mass of the solvent. I'm going to do that by getting the difference between these two. So the difference between 128.5 is 71.5. That's my mass. Now for molality, it's moles per kilogram. I'm going to put my moles, 0.206, divided by my kilograms. Again, this is in grams, so I got to divide it by 1,000. And I get 0.0715 kilograms, and I find that my solution is 0.288 molal. And then finally, I need to get my mole fraction. So for mole fraction, the last thing I need is fill in these spots here, because I need to know the moles divided by the total moles, moles divided by total moles. So I need to use my molar mass of water in order to figure out the number of moles of water I have. So I have 71.5 grams of water at 18.5. Then I'm going to have almost 4 moles of water. Do the math to find out what the total is. And then mole fraction is moles divided by total moles. So mole fraction is simply 0.206 divided by 418. And again, it's not a percent. You don't multiply times anything. It's a fraction. The larger the number, closer to 1, the closer it is to being a pure mixture. Okay, so next, you try. I have a solution that's 1.22 molar, and it has a density of 1.04 grams per mil. I want you to calculate the molarity, mole fraction, and mass percent. Go ahead and pause this video to try it on your own, and then you can start it back up, and I'm going to show you how to do this one. So go ahead and hit the pause button now. I'll wait. See you on the other side. Hit the pause button. Don't cheat. Okay, you all finished now? Good. Let me show you how to do this problem. So first thing you do is fill in the table with the 1.22 moles per milliliter. That should be moles, not M. And then you're going to do your little conversions. First one you're going to do, to change it over mass percent, you're going to change your moles to grams using your molar mass of the substance, and then divide it by, then also determine your number of grams of solution using your density, and then calculate your mass percent to be 65 divided by the 1,000, and it's like 6%. 6% of the total solution is your compound. Then next, you're going to go ahead and figure out the mass of the solvent by figuring out the difference to be able to determine the molality, moles of solvent divided by kilograms of solvent, and you get 1.26. And then finally, the last one is to get your mole fraction. Just like before, change your mass into moles, add these together, get the total moles, and get a mole fraction of 0.221. So how'd you do? Pretty good? So hopefully you see how this might be helpful. If you're given one concentration unit of the four, you should be able to solve for the other three without any difficulty. So next time we get together, I'm going to put together something for the beginning part of chapter 5, which is gases. I may actually include somebody else's video this time, because gases are one of those things where it's really helpful to see a lot of examples and to have more visuals than the PowerPoint. So you might not get to hear my voice next time, but We shall see. Anyway, until next time, be safe, wash your hands, and always remember and never forget, sig figs matter. See ya.